In this video, we will develop formulas for exponential functions when we know their one-unit growth factor as well as a pair of reference values. So suppose f is an exponential function with f of 0 equal to 4 and a one-unit growth factor of 1.2. This 1.2 means that anytime x changes by 1, y will become 1.2 times as large. So if x varies from 0 to 1, y starts at a value of 4 and then becomes 1.2 times as large. On the other hand, if x varies from 0 to 2, a change of 2 units, then y will start at 4 and become 1.2 squared times as large, because our 2-unit growth factor is 1.2 squared. And therefore, as x varies from 0 to 2, y starts at 4 and then becomes 1.2 squared times as large. Now in general, if x varies from 0 to any value x, so a change of x units, then y will start at a value of 4 and then become 1.2 to the x times as large, because our x unit growth factor is 1.2 to the x. So if x varies from 0 to its new value of x, then y starts at a value of 4 and then becomes 1.2 to the x times as large. And therefore, we can say that f of x is equal to 4 times 1.2 to the x. Let's generalize this way of thinking. So suppose f is an exponential function with f of 0 equal to a and a one-unit growth factor of b, meaning that anytime x changes by 1, y will become b times as large. So in this case, if x varies from 0 to 1, a change of 1 unit, then y will start at a and become b times as large. So as x varies from 0 to 1, y starts at a and then becomes b times as large. And more generally, if x varies from 0 to its new value of x, a change of x units, then y will start at a value of a and then become b to the x times as large. So as x varies from 0 to its new value of x, y starts at a value of a and then becomes b to the x times as large. And therefore, f of x is equal to a times b to the x, where a is our initial value of y, or our value of y when x equals 0, and b is our one-unit growth factor. Let's look at another example. So suppose f is an exponential function with f of 1 equal to 13.5 and a one-unit growth factor of 1.5. So in this case, we know the value of y when x equals 1 instead of when x equals 0. So a one-unit growth factor of 1.5 means anytime x changes by 1, y becomes 1.5 times as large. So if x varies from 1 to 2, a change of 1 unit, then y will start at 13.5 and then become 1.5 times as large. So as x varies from 1 to 2, y starts at 13.5 and then becomes 1.5 times as large. Now let's imagine x varying from 1 to its new value of x. This is a change in x of x minus 1. So the final value of x is x, initial value of x was 1, so that's a change of x minus 1. And our x minus 1 growth factor is 1.5, which is our one-unit growth factor, to a power of this change of x. So anytime x changes by x minus 1, y becomes 1.5 to a power of x minus 1 times as large. So we can say that as x varies from 1 to x, y starts at 13.5 and then becomes 1.5 to the x minus 1 times as large. And therefore, f of x is equal to 13.5 times 1.5 to the x minus 1. Let's generalize that previous way of thinking. Suppose f is an exponential function with f of x1 equal to y1, and we have a one-unit growth factor of b. If x varies from x1 to its new value of x, that's a change of x minus x1. And our x minus x1 unit growth factor is b to the x minus x1. So anytime x changes by x minus x1, then y will become b to the x minus x1 times as large. So as x varies from x1 to its new value of y varies from y1 to a value that is b to the x minus x1 times this large. And therefore, we could say that f of x is equal to y1 times b to the x minus x1. And this is a very general way of writing the formula for an exponential function when we know any pair of values and we know the 1 unit growth factor.